Okay, in this video, we're going to talk about section 4.9 dealing with antiderivatives. And out of that section, we're going to be finding general antiderivatives and indefinite integrals. Also, we'll find particular antiderivatives and solve initial value problems. So what this section does, it's going to introduce us to something called integration, which is going to be in chapter 5. Okay, so now, up until now, we've been taking derivatives of functions here, and we learned various methods of taking the derivatives of various types of functions. Now we're going to be going in the opposite direction. In this case, we're going to be talking about antiderivatives. So the goal of differentiation is to find the derivative or f prime of a given function f. So now the reverse process is called antidifferentiation. That's going to be equally important as well. So if we're given a function called f, we look for an antiderivative function called capital F, whose derivative will be lowercase f. That is, a function f such that capital F prime is equal to f. And here's the definition of the antiderivative. So a function called capital F is an antiderivative of lowercase f on an interval I, provided that f prime of x, capital F prime of x, is equal to f of x for all x in that interval I. So this section, we're going to revisit derivative formulas developed in previous chapters to discover corresponding antiderivative formulas. Okay, that's the basis of section 4.9. All right, so here we're going to be thinking backwards here. Let's say we have this function d, the derivative with respect to x of x equaling to 1. It does imply that the antiderivative of f of x equals 1 is capital F of x equaling to x. And that's because if I take the derivative of capital F of x, I would get lowercase f of x, because the derivative of x is, of course, 1. Using that same logic, we can write this. The derivative with respect to x of x squared is equal to 2x. That would mean that the antiderivative of f of x equals to 2x is equal to capital F of x equaling to x squared. Also, the derivative of sine of x with respect to x would be cosine of x. That would mean the antiderivative of f of x equaling to the cosine of x would be capital F of x equaling to the sine of x. Okay, so each of these proposed antiderivative formulas is easily checked by showing that capital F prime would be equal to f. But then we have a question that we need to ask ourselves. Does the function have more than one antiderivative? Okay. So we can focus on something like f of x is equal to 1 and the antiderivative of f of x equaling to x. Okay? Now, let's just say this. Since capital F of x does equal to x and that derivative, which is this, does equal to 1. But let's say capital F of x is equal to x plus, let's say, 6. And if I take its derivative, I would get this back. It will be 1, because the derivative of x is 1, and the derivative of a constant, of course, is 0. Or, let's say capital F of x is x minus, let's say, 74. And if I take its derivative, I'm also going to get lowercase f of x, which is 1. Or capital F of x will be x minus, I'll say pi. Pi is a constant. The derivative of that constant is 0. So the derivative of capital F of x equaling to x minus pi would still give me 1. So there are infinitely many derivatives for capital F of x equaling to x. Okay. And because the derivative of a constant c is 0, we see that capital F of x equals to x plus c is also an antiderivative of lowercase f of x equals to 1. And we can easily check by just taking the derivative here of x plus that constant. That would give you 1, which is lowercase f of x. So here you can see that f of x equals 1 has an infinite number of antiderivatives here. And it also works the same way for capital F of x equals to x squared plus c. It has, you take its antiderivative, or take the derivative of that, you'll get f of x equals to 2x, or any function of the form f of x equal to sine of x plus c. Take its derivative, you're going to get f of x equals to cosine of x. And c can be an arbitrary constant. Okay? So in this theorem, we do have what they call the family of antiderivatives here. So we let f be any antiderivative of f on the interval I, then all the antiderivatives of f on I have the form f plus c. And here c will be your arbitrary constant. Okay? So here we're going to be dealing with a family of antiderivatives. Now if you look at example 1 on the next page, here we can use what we already know about derivatives to find all antiderivatives of the following functions. Like for lowercase f of x is equal to 3x squared. And part B, f of x is equal to 1 over 1 plus x squared. And C, f of t is equal to sine of t. Okay. Now, if you pretty much look in the middle of this handout here, we can find out what those antiderivatives are going to be. Like for lowercase f of x is equal to 3x squared, that would be, of course, capital F of x. That will, of course, be x cubed. And the reason for that is if you bring the exponent down, the 3 will go in front, copy the x over to the 1 less power, that would give you 3x squared. And of course, for all antiderivatives, it will have to be plus c. Okay. And then in part B, you got f of x is equal to 1 divided by 1 plus x squared. Now, if you're familiar with the 6 trigonometric functions and their derivatives, you will see that the derivative of the inverse tangent will give you this back, 1 over 1 plus x squared. So that means capital F of x will have to be the inverse tangent of x plus c. Inverse tangent of x plus c. Now part C is the one that's kind of tricky here because you're going to have to think about this one right here. F of t is going to be sine of t. That would mean capital F of t would be something like this. Negative cosine t plus c. And that is, if you were to take the derivative of the cosine of t, you'll get negative sine of t. But then that negative sine of t will give you back the positive sine of t. And I might want to go ahead and write this out so that way you'll see that if you take the derivative with respect to x of negative cosine of t plus a constant, bring this negative over, the derivative of the cosine of t is negative sine of t. And then negative times a negative will make that positive sine of t. So that means the antiderivative of sine of t will be negative cosine of t plus c. Okay? All right, now we're going to talk about indefinite integrals here. Now the notation that we use for the derivative with respect to x of f of x, that means you take your derivative of f of x with respect to x. So now we need some notation for the antiderivatives, okay? And here we're going to use what they call the indefinite integral, okay? So the notation that means to find the antiderivatives of f, we use the indefinite integral. That's this symbol, f of x equal to dx. Okay? Now, notation of that would be this, of course, the integral of f of x dx. That would be equal to capital F of x, and then plus the constant. So that's the notation that we use here. Now, what do each of these parts mean? Or what do they represent? This symbol that you see here looks like an elongated S, which actually means the sum. That means that's your integral sign. That's your integral sign. This f of x right here, we call that the integrand, integrand. And then dx, in this case, represents the variable of integration. And it's not necessarily restricted to just x or dx. It could be dt, it could be dv, or it could be dr, or whatever. Because these two are the same. If this is x, then they use dx. If it's a t, then it'll be dt. The capital F of x, we call that the antiderivative. And then this plus c that you see here represents the constant of integration. The constant of integration. And with these indefinite integrals, I will tell you, when you do the indefinite integral, you must include that plus c. Okay? So those are just the parts of what indefinite integrals are. Okay? Now, we're going to begin taking integrals by using what they call the power rule. We do have the power rule for taking the derivatives. If you recall, when you use the power rule for derivatives, you always bring that power in front and then copy the variable or the expression over. We'll just say the variable in this case to the one less power. Here we're going to do this in the reverse order for indefinite integrals here. So the power rule for indefinite integrals is this. We have the integral of x raised to some power p. And as long as p is not equal to 1, we can do this power rule by increasing the power by 1 and then dividing it by that new power, p plus 1. And then we include the plus c for our indefinite integral here. Okay? And of course, p cannot be equal to 1, because if it was equal to 1, then we would get a 0 in the denominator, and this power rule would not work for p being equal to negative 1. Okay? And notice that if p was equal to negative 1, then f of x, capital F of x, would be undefined. Okay? And of course, the antiderivative of f of x is equal to negative 1. We'll discuss that part a little bit later. And then the case if p was equal to 0, that's this exponent here, that's going to say that the integral of 1 dx will be equal to x plus c. That's very important. Okay, now on the next page, any indefinite integral calculation can be checked by differentiation, because keep in mind, taking the derivative is the opposite of taking the integral. So that means if you want to check, you can take the derivative of what you got, and you must end up getting the integrand that you started off with. Okay? Now, this next theorem talks about the constant multiple and sum rules. We have that for derivatives as well that we talked about back in chapter 3. So we have that with differentiation and with integration as well. the constant multiple rule states this: if you have the integral of c times f of x dx, and c is a real number, you can pull that constant out in front of the integral sign and write that as c times the integral of f of x dx. And next is the sum rule, which is also the sum and the difference rule, because this also works if this was a minus sign in between. The integral of f of x plus g of x dx, what you can do here, if you have the integral of the sum, I can take the sum of the individual integrals. I can do the integral of f of x dx plus the integral of g of x dx. That's the sum rule, or the sum and difference rule, because this also works if you had a minus sign in between. Okay, take a look at example 2. Let's say I want to determine the following indefinite integral, and I want to check by differentiation. All right, here we got the integral of 5x to the 9th minus 11x to the 21st dx. Okay. Now notice that the integral of the difference, I can write that as a difference of the individual integrals. So that means I can write this as the integral of 5x to the 9th dx minus the integral of 11x to the 21st dx. Okay? And I also can apply that constant multiple rule by pulling the constant or the coefficient of my variable in front of that integral sign. So like the integral of 5x to the 9th dx, that 5 is a constant. I can pull that out in front and say 5 times the integral of x to the 9th dx. And the same holds true here, well, minus, the same holds true here for the integral of 11x to the 21st dx. I can take the 11 and pull that out in front, so it'll be 11 times the integral of x to the 21st dx. And from here, we can apply that power rule for each of these integrals here. So I'll bring down the 5. So to integrate x to the 9 dx, I increase the power by 1, so it'll be x to the 9 plus 1 is going to be 10. And then that's divided by that new exponent, which is 10. And then minus 11 times increase, well, bring the x down and increase the power by 1. So if I add 1 to the 21, it will be 22. That will be divided by 22, which is that new exponent. And since this is an indefinite integral, I must include plus c. And now let's simplify this a bit. If I divide this 5 into this 10 in the denominator, that's going to go 2 times. So 5/10 reduces to 1/2 times x to the 10th minus, divide this 11 into this 22 in the denominator, that's going to go 2 times as well. So 11 over 22 reduces to 1/2. And then x to the 22nd plus c. Okay. Now, if I want to check that answer by differentiation, what I can do here is take this derivative of that expression right there. So the derivative with respect to x of 1/2 x to the 10th minus 1/2 x to the 22nd plus c. So here I can take the derivative of each term in the parentheses. So I'll have 1/2, and then bring down the exponent in front of the x, copy the x over to the 1 less power. 10 minus 1, that would be 9, minus 1/2. And then for x to the 22, bring down the exponent of 22, copy the x over to the 1 less power. 22 minus 1 will be 21. And the derivative of a constant, whatever that is 0. Now if I take 1/2 of 10, that's going to be 5. So I have 5x to the 9 minus a half of 22 is 11, so it'll be 11 x to the 21st. Compare that to what I have here. It must be equal to the integrand that I have here. So that tells me I have successfully taken the integral of that expression, which is 1/2 x to the 10th minus 1/2 x to the 22nd plus c. Or they might want it like this: x to the 10 over 2 minus x to the 22nd over 2 plus c. Okay. All right, let's look at example 3. Here we got this. We got the integral of 9 divided by the square root of x plus 9 square root of x. What I'm going to do here first is write the square root of x in its equivalent exponential form. Okay, so here I'm going to bring over the integral sign of 9 over the square root of x. That's going to be x to the 1/2 power. Keep in mind that the x has the understood exponent of 1. The index is the understood 2, so it'll be 1 over 2, x to the 1/2. Plus 9, and the square root of x again will be x to the 1/2 dx. Now I'm going to use that sum rule for integrals. So I have this integral of the sum. That will be the sum of their individual integrals. So here I'm going to have the integral of, let's see, 9. But if I pull that x to the 1/2 out of the denominator, this will be x to the negative 1/2 dx plus the integral of 9 x to the positive 1/2 dx. And of course I can use the constant multiple rule on each of these terms here. This 9 is the coefficient of x to the 1/2 that can come outside the integral, so it'll be 9 times the integral of x to the negative 1/2 dx plus, same thing here, I can use the constant multiple rule by pulling the 9 on the outside of the integral sign, so it'll be 9 times the integral of x to the 1/2 dx. And then we can take the integral of each one of these. So if I bring down the 9, here I'm going to increase the power by 1. So this will be x to the, now keep in mind this is negative 1/2 plus 1. And if you want to do this in the calculator, clear this out. Negative 1 divided by 2, and then plus 1. Hit your math key and select number 1 for fraction, and then hit enter. That will give you the new exponent of 1/2. And that's going to be divided by 1/2, which is your new exponent, plus 9 times. For that x, for the integral of x to the 1/2 dx, I increase the power by 1 on this one as well. So I have 1 divided by 2 for 1/2 plus 1. Then hit the math key and number 1 for fraction. That would be x to the 3/2 power. That's divided by your new exponent of 3/2. And of course I need to include that plus c since I'm taking the indefinite integral. Alright, so I need to simplify this a bit. I need to do 9 divided by 1/2. If you want to, you can do this in the calculator, 9 divided by, and then left parentheses, 1 divided by 2. This will end up being 18. So I'm going to have 18 x to the 1/2 plus, and this one will be 9 divided by 3/2. So it'll be 9 divided by 3 divided by 2. This is going to end up being 6. So I have 6 x to the 3/2 plus c. And that x to the 1/2 there, I can write that in radical form as 18 times the square root of x. And then plus, I'll leave that as 6x to the 3/2 plus c. So this is the integral of 9 over the square root of x plus 9 square root of x dx. 18 square root of x plus 6x to the 3/2 power plus c. Okay. All right, let's look at another example. Okay, let's say we had the integral of 6 over t squared minus 7t to the 5th dt. And I'm going to write this using negative exponents in this case. So I have the integral of, I have the 6 in the numerator. If I pull that t squared out of the denominator, it will be t to the negative 2 minus 7t to the 5th dt. Now I'm going to use the sum and difference rule. We have the integral of the difference. I can write that as the difference of the individual integrals. And I'm also going to use the constant multiple rule as well, because I have coefficients in front of the t's here. So that 6 here can go outside of that integral sign, so it'll be 6 times the integral of t to the negative 2 dt, and then minus, for the 7t to the 5th, if I pull the 7 on the outside, so it'll be 7 times the integral of t to the 5th dt. Now keep in mind, you don't have to write every single step that I have here, because once you get the hang of it, once you get the idea about how to do these integrals and how to use those rules that I just gave you, then pretty much you can skip 1 or 2 steps, but don't skip too many steps here. All right, so bring down the 6. For the integral of t to the negative 2 dt, increase the power by 1. So it'd be t to the negative 2 plus 1, which will be negative 1, divided by that new exponent of negative 1. Plus, bring down to 7. For the integral of t to the negative 5th dt, we increase the power by 1, so we add 1 to the 5. That would give us t to the 6, and it'll be divided by that new exponent of 6. And then plus c. Then if I simplify this, 6 divided by negative 1 will be 6. So it'll be negative 6t to the negative 1 plus 7 divided by 6, we'll leave that as 7 over 6 times t to the 6 plus c. Okay. And sometimes they might want this as negative 6 over t plus 6t to the 6 plus c. That t to the negative 1 can be written as 1 over t using positive exponents. And that depends upon what your instructor wants. Okay, example 5. Let's say I want to find the integral of 6x plus 5 quantity squared, dx. Okay. In this case, we only know the power rule for integration. So what that means here is this. I need to go ahead and multiply this out first, and then find out what that integral is going to be. So in this case here, if I take the integral, well, if I multiply this out, 6x plus 5 quantity squared means 6x plus 5 times 6x plus 5. And then we're going to use the FOIL method to multiply two binomials here. So if I do first times the first, 6x times 6x, that's 36x squared. Outer will be 6x times that plus 5 will be a plus 30x. Integral 5 times 6x will be plus 30x. And then 5 times 5 will be plus 25. For method is first, outer, inner, and then last. So if I combine like terms here, I have 36x squared plus 30x, and 30x is 60x plus 25. So in this case here, I have the integral of this right here, 36x squared plus 60x plus 25 dx. And notice that expression is in parentheses. Now let's go ahead and use the sum rule for integration by taking the sum of their individual integrals. So this will be the integral of 36x squared dx plus the integral of 60x dx plus the integral of 25 dx. Okay, so now, using the constant multiple rule, I can pull the constant out in front. So it'll be 36 times the integral of x squared dx plus 60 times the integral of x dx plus 25 times the integral dx. Okay, so now, using the power rule, bring down the 36. Increase the power by 1 and divide that by the new exponent. So if I increase the 2 by 1, it'll be to the third, x to the third, raised to the 3, that's your new exponent, plus 60 times, this is x to the understood 1. If I increase that power by 1, it'll be 1 plus 1, which is 2, so it'll be x squared divided by 2, that's your new exponent, plus 25 times, the integral of dx, or 1 dx, would just be x. And of course, I need to include the plus c. Can't leave that out. Now, let's simplify this a bit. Divide 3 into 36, that will go 12 times. So it'll be 12x cubed plus divide 2 into 30. That's going to go, 2 into 60, I gave it away, that goes 30 times. So it'll be 30x squared. And then plus 25x plus c. So the integral of the quantity 6x plus 5 squared dx will be 12x cubed plus 30x squared plus 25x plus c. Okay. All right, example 6 looks like this. Let's say I want to determine the following indefinite integral. And let's say I want to check by differentiation. Here I got the integral of 4m times 5m squared minus 7m dm. So the first thing I'm going to do here is use what they call the distributive property. In other words, I'm going to distribute the 4m over the 5m squared times 7m. So if I do 4m times 5m squared, that's going to be 20m cubed minus 4m times the 7m will be 28m squared times, dm. Okay? So first I distribute the 4m over the 5m squared minus 7m to get this. Now we're going to use the combination of the constant multiple rule and the sum rule to break this apart. That 20 is my coefficient for m cubed. I can pull that on the outside, so it'll be 20 times the integral of m cubed dm minus, same thing here, I can pull the 28 out in front of the integral of m squared dm. Okay, so I'm taking the integral of each part and using the constant multiple rule. So here's what I'm going to have here. Bring this 20 down. If I integrate m cubed dm using the power rule, I increase the power by 1. So it'll be m to the 4th divided by that new exponent of 4. Then minus 28 times, use the power rule again by increasing the power by 1. So it'll be 2 plus 1, that's going to be 3. So it'll be m to the 3rd divided by 3. And of course I need to include plus c. All right, simplify this a bit. Divide 4 into 20. That's going to go 5 times. So this will be 5m to the 4th minus, and I will leave 28 divided by 3 as 28 thirds as an improper fraction, times m cubed plus c. So the integral of 4m times the quantity 5m squared minus 7m dm would be 5m to the 4th minus 28m to the 3rd plus c. Okay. Okay, example 7 looks like this. Now here we got exponents that are in the form of a fraction. Okay. And by the way, before I go into that, check your work by differentiation. I will leave the check up to you all. So if you want to go ahead and check, you just take the derivative of this. You should, well, not necessarily get this back, but you should get this part right here. All right, now in example 7, we got the integral of 5x to the 1/3 plus 2x to the negative 2/3 plus 11 dx. Using the sum rule and the constant multiple rule, I have this. For the 5x to the 1/3, I will put the 5 in front times the integral of x to the 1/3 dx plus for the 2x to the negative 2/3, I'll pull the 2 out in front. It'll be the integral of x to the negative 2/3 plus, let's see, 11 dx, the integral of that, I'll pull the 11 out in front. So it'll be 11 times the integral dx. Okay, so pull the 5 out in front. For the x to the 1/3 dx, if I integrate that, I'll increase the power by 1. So it'll be x to the, and I'll show you again, 1/3 plus 1. So it'll be 1 divided by 3 plus 1. And as a fraction, you hit the math key and then fraction, you'll get 4/3. So it'll be x to the 4/3 divided by that new exponent of 4/3 plus 2 times here for the integral of x to the 2/3, and I left off something that's very important, dx. Integral of x to the negative 2/3 dx. You increase the power by 1. So this will be negative 2 divided by 3 plus 1. Hit your math key and then number 1 for fraction. That would give you 1/3. So the x to the 1/3 divided by your new exponent of 1/3 plus 11 times. The integral of dx will be x plus c. All right, so now let's simplify this a bit. If I do 5 divided by 4/3, I can do that in the calculator. 5 divided by, and then in parentheses, 4 divided by 3. And then I'm going to do the math key, and then number 1 for fraction. This will give you 15/4. So it'll be 15 over 4 times x to the 4/3 plus 2 divided by 1/3 will be 2 divided by, then left parentheses, 1 divided by 3, close parentheses, math key, and then number 1 for fraction. I end up getting 6 as a whole number. So that'll be 6x to the 1/3 plus 11x plus c. and I will go no further than that. Okay? And I will leave the check up to you on this. Because once you do the derivative of that, you should get this back as your integrand. All right, example 8 looks like this. You got the integral of 7 times the 12th root of x dx. 7 times the 12th root of x dx. I'm going to write the 12th root of x in exponential form, so I'll bring the 7 over. The 12th root of x will be x to the exponent for the x is the understood 1. My index is a 12, so that's your denominator. And then dx. So I have 7x, the integral of 7x to the 1/12 dx. Well, using the constant multiple rule, I can pull the 7 out in front, so it'll be 7 times the integral of x to the 1/12 dx. And then I can integrate x to the 1/12 dx. So bring down the 7, increase the power by 1, and then divide by the new exponent. Here's what I'm going to do. 1 divided by 12 plus 1, because I'm increasing the power by 1. Hit the math key and then number 1 for fraction. That would give you 13/12, so my exponent will be 13 over 12. Divided by 13 over 12. And then plus c. Now, if I do 7 divided by 13/12 in the calculator, 7 divided by, now I'm going to put 13/12 in parentheses, so left parentheses, 13 divided by 12, close parentheses, then hit your math key and then number 1 for fraction, you'll get 84/13. So this would be 84/13 times x to the 13/12 plus c. And now, again, I'll leave the check up to y'all. So pretty much, you should be able to get, let's say, this back. If you get that back, then that tells you that you have done the integration correctly. All right, example 9 looks like this. Here we got the integral of 6 over x to the 9th plus 4 minus 8 over x squared dx. All right, let's use the sum rule on this. Or better yet, let's pull these exponents, pull these variables out of the denominator. So I'm going to have the integral of 6. The x to the 9th in the denominator, if I take that out, it will be out of that denominator, it will be x to the negative 9, and then plus 4, minus the 8, and if I take the x squared out of the denominator, it will be x to the negative 2 dx. Okay. Here I'm just writing them using negative exponents in this case. So, use the sum and the constant multiple rules for integration. For this term right here, I'll pull the 6 out in front, so it'll be 6 times the integral of x to the negative 9 dx plus that 4 can be pulled outside the integral sign, so it'll be 4x, just the integral, 4 times the integral dx minus the integral, for the 8 to the negative 2, let's pull the 8 out in front, so it'll be minus 8 times the integral of x to the negative 2 dx. All right, so the next thing I'm going to do here is integrate each part. For the integral of x to the negative 9 dx, I'll increase the power by 1, so it'll be negative 9 plus 1, that'll be x to the negative 8. And then divide that by your new exponent of negative 8. Plus 4 times the integral of dx, of course, that's just going to be x. And then minus 8 times For the integral of x to the negative 2 dx, we increase the power by 1. So it'll be x to the negative 1. That's negative 2 plus 1, negative 1. Divide that by your new exponent of negative 1. And then, of course, include the plus c since it's an indefinite integral. Now, let's see what we can do here. If I do 6 over negative 8, in simplest form, negative 6 divided by 8, and then math, number 1, for fraction, it'll be negative 3/4. X to the negative 8, then plus 4x. The minus 8 divided by that negative 1 would be plus 8. X to the negative 1, and then plus c. Now, if I rewrote this using positive exponents this time, I'll have the negative 3 in the numerator. The 4 stays in the denominator, but if I put that x to the negative 8 in that denominator, it will be x to the positive 8. Then plus 4x, and then plus 8 stays in the numerator. That x to the negative 1, if I put that in the denominator, it will just be x to the 1, or just x, plus c. So this is what your integral will be for the integral of 6 over x to the 9th plus 4 minus 8 over x squared. Negative 3 divided by 4x to the 8th plus 4x plus 8 divided by x plus c. Okay. Example 10 looks like this. Let's say we had the integral of 3x cubed plus 8x squared divided by x dx. Well, I do have a monomial in the denominator, so I can take each term in the numerator and divide that by your x. So here's what I have. The integral of 3x cubed divided by x plus 8x squared divided by x, and then dx. So if I simplify this, 3x cubed divided by x would just be 3x squared. Plus 8x squared divided by x, that would just be 8x. And then dx. And then use the sum rule and the constant multiple rule for your integration. So for that first term, 3x squared, I'll pull the 3 out in front, so it'll be 3 times the integral of x squared dx. Plus, for the second term, 8x, 8 can go outside the integral sign, so it'll be 8 times the integral of x dx. Okay. So now let's go ahead and integrate each part. Bring down to 3. Using the power rule, I increase the power by 1, so it'll be x to the 2 plus 1, which will be 3, divided by your new exponent of 3, plus bring over the 8. Increase the power for the integral of x squared, for the integral of x dx, I'm sorry. This is the understood one. We increase the power by 1, so it'll be 1 plus 1, which will be 2, so it'll be x squared over the new exponent of 2, plus c. Now, if I simplify this, these 3's divide out. I'm left with x cubed plus, divide 2 into this 8. That goes 4 times. So I have 4x squared, and then plus c. So that will be the integral of 3x cubed plus 8x squared divided by x dx will end up being x cubed plus 4x squared plus c. Okay. All right, next we'll look at indefinite integrals of trigonometric functions. So somewhere back in chapter 3, we did talk about the derivatives of our 6 trigonometric functions here. If you notice on the left-hand side are your 6 trig functions. The right-hand side would be their corresponding integrals. So the derivative with respect to x of sine of x, that's the cosine of x. That would mean the integral of cosine of x dx will be sine of x plus c. And then next would be the derivative with respect to x of the cosine of x, that's negative sine of x. That would mean the integral of sine of x dx will be equal to the negative cosine of x plus c. Now, keep that in mind, that you have negative cosine of x plus c as the integral of sine of x, because if you took the derivative with respect to x of negative cosine of x plus c, you'll have the negative sign here. The derivative of the cosine is negative sine of x, so I have negative of negative sine of x, and the derivative of the constant is 0. Negative times a negative will be a positive, so it'll be sine of x, which is this integrand that we have here. That's why it's like that. And then for the derivative with respect to x of tangent of x, that's just secant of x, secant square of x. So that means here, if we take the integral of secant square of x dx will be tangent of x plus c. And then number 4, the derivative with respect to x of the cotangent of x is negative cosecant square of x. So the integral of the cosecant square of x dx will be negative cotangent of x plus c. That's similar to with the integral of sine of x dx being negative cosine of x. That's why the negative sign is there. Then the 5th one is the derivative of the secant of x. That's secant x tangent x. The integral of the secant x tangent of x dx will be secant of x plus c. And then the derivative of the cosecant of x with respect to x will be negative cosecant x cotangent of x. So if I take the integral of cosecant x cotangent x dx, that's going to be negative cosecant x plus c. So do be familiar with those integrals as well, because we'll be using those to find their respective integrals, like in these two examples that I have here. Starting with example 11, we want to determine the following indefinite integral, and we're going to check this one by differentiation. So here we got the integral of the cosecant square of theta plus 8 d theta. So if I break this up, I have the integral of the cosecant square of theta plus the integral of 8 d theta. And I could do this. Integral of cosecant squared theta, and I left this off, d theta. And then that's a plus sign. Plus, pull the 8 out in front of the integral sign, so I have 8 times the integral of d theta. Now the integral of the cosecant square of theta, d theta, going back to this right here, integral of cosecant square x dx, that's negative cotangent of x. So this will be negative cotangent of theta. Plus 8 times the integral of d theta would just be theta, and then plus c. Okay, that's the integral. Now, if you want to check this, we're going to do that as well. So here's what the check looks like. Take the derivative with respect to x of negative cotangent theta plus 8 times theta plus c. Well, bring this negative sign over. The derivative of the cotangent of theta is negative cosecant square of theta. Derivative of the cotangent of theta is negative cosecant square of that angle. Plus the derivative of 8 with respect to theta I should say this right here because this is in terms of theta. So the derivative of 8 theta would be 8, and the derivative of a constant is 0. Okay. So negative cosecant square of theta would be cosecant square of theta, and then plus 8, which is this integrand that I started off with. Okay. So that's how we check by differentiation. And in example 12, let's say we got the integral of the secant square of x plus 8 dx. Well, if I integrate each term, this will be the integral of the secant square of x dx plus 8 times the integral of dx. And here I'm pulling the 8 out in front using the constant multiple rule. Now, using that table that I showed you, the integral of the secant square of x dx, here it is, integral secant square of x dx, that's the tangent of x. So here, this will be tangent x plus 8 times the derivative of the integral of dx would just be x, and then plus c. So the integral of secant square x dx is tangent of x. The integral of 8 times the integral of dx will be 8x, and then plus c. Okay, and again, we can do the check by taking the derivative with respect to x of tangent of x plus 8x plus c. Well, the derivative of the tangent of x is secant square of x plus the derivative of 8x is 8. And the derivative of the constant is 0. So this is the same as the integrand that we have, secant square of x plus 8. Okay? So that's how we use those 6 trigonometric functions to find integrals of those. Now we do have other indefinite integrals here on the next page. And that's this. On the left-hand side, you see their derivatives here. The first two deals with exponential and logarithmic expressions here. The last 3 deals with inverse trig functions. So with the derivative of e to the x, that's of course e to the x, the easiest derivative to take. Now, if you do the integral of e to the x dx, again, that's the easiest integral to take, e to the x plus c. And then the next one, the derivative with respect to x of the natural log of the absolute value of x, that's 1 over x. So the integral of dx over x, or 1 over x dx, will be the natural log of the absolute value of x plus c. Natural log of the absolute value of x plus c, that's your integral of dx over x. The next 3 are inverse trig functions. The derivative with respect to x of the inverse sine of x, that's going to be 1 over the square root of 1 minus x squared. So if we had the integral of dx over the square root of 1 minus x squared, that's going to be the inverse sine of x plus c. And then the next one, the derivative of the inverse tangent of x with respect to x, that's 1 over 1 plus x squared. So the integral of dx over 1 plus x squared would be the inverse tangent of x plus c. And then we have the derivative of the inverse secant of the absolute value of x with respect to x. That's going to be 1 divided by x times the square root of x squared minus 1. So that means here your integral of dx divided by x square root of x squared minus 1, that would be the inverse secant of the absolute value of x plus c. So these are your other indefinite integrals. And we'll be using those to solve some of these examples here, like in example 13. Here we got the integral of 1 over 10y dy. The integral of 1 over 10y dy. Now what I would do here, since I got 1 over 10, that's a constant, I can pull that constant out in front. So it'll be 1/10 times the integral of, let's say, put the dy in the numerator, over y. Well, that looks similar to this one right here, the integral of dx over x. But here we're using y, so it'll be ln of the absolute value of x plus c. So if I take the integral of dy over y, that's going to equal to, I'm going to bring the 1/10 over, natural log of the absolute value of y plus c. Notice you have to have the absolute value there because of the domain for the natural logarithm. It can't be negative and it cannot be 0. All right, example 14 looks like this. Let's say I want to determine the following indefinite integral, and I'll leave the check up to you all if you want to. The integral of 6 divided by 49w squared plus 49 dw. Let's do this. I have the integral of 6 divided by, notice in the denominator I need a common factor for 49w squared and 49, which is 49. So if I factor out the 49, I would get this, w squared plus 1. Now bring over that dw. Now we have the integral, well actually, I got 6 over 49. That's a constant. I can take that out of the integral sign and pull that out in front. So it'll be 6 over 49 times the integral of 1 over w squared plus 1 dw. So now I got 6 over 49. And in this case here, that integral of 1 over w squared plus 1 dw, that's pretty much similar to this one right here. It's just the order that's different. So if I take that integral, it will be the inverse tangent of x plus c. And since I'm dealing with w here in this case, I will have the inverse tangent of w, and then plus c. And that would be as far as I can go with that problem. So that integral will be 6 over 49 times the inverse tangent of w plus c. Okay. All right, let's look at the next example here. Let's say we have the integral of 6 plus u divided by u du. In this case here, I have a monomial in the denominator. I can take each term in the numerator, divide that by the u in this case. So I can break this up as the integral of 6 over u plus u divided by u du. So here this will be the integral of 6 over u plus u divided by u will be 1. Now this will remain in parentheses, times du. And then, using the sum rule and the constant multiple rule, for this part, that's 6 over u, I can pull the 6 out in front, so it'll be 6 times the integral of du over u plus, for the 1, I can pull the 1 out in front, so it'll be 1 times the integral of du. Now, in this case here, the integral of du over u, that of course follows this rule right here. Integral of dx over x, which is be the natural log of the absolute value of x plus c. But here I'm using u, so that means I have 6 times the natural log of the absolute value of u plus 1 times the absolute 1 times the integral of du would just be u. So 1 times u will be u plus c. So the integral of 6 plus u divided by u du will be 6 ln of the absolute value of u plus c. Okay, example 16. Let's say we want to determine the indefinite integral here. And again, I'll leave the check up to you if you like. Let's say we got the integral of 7 divided by the square root of 1 minus x squared dx. Let's do this. That 7 is a constant, so I can pull the constant out in front. So it'll be 7 times the integral of 1 divided by the square root of 1 minus x squared dx. Or if I want to, I can do this. 7 times the integral of dx in the numerator. That would be divided by the square root of 1 minus x squared. And in this case here, this follows or matches up with this right here. So the integral of dx over the square root of 1 minus x squared would be the inverse sine of x. So here, I'll have 7 times the inverse sine of x plus c. Okay. All right, so that's pretty much how we take integrals of various functions. So do be familiar with those two tables that I gave you, including the power rule, and then you have your constant multiple rule, and then you have your sum rule. Be familiar with those, especially the power rule, because you'll be using a lot of that. And as you can see, that's a lot of that has been done in this video here. All right, now, this last thing I'm going to talk about in this video would be an introduction to differential equations. Now, I'm just going to talk about things like the initial value problems here. There is a whole course that's offered, I think, at the 2000 at some community college, or at the 3000 or 4000 level at many universities across the country that talk about explicitly just differential equations. Okay? Now, an equation involving an unknown function and its derivatives is called a differential equation. All right, so let's say we want to consider a more general differential equation of the form f prime of x equal to g of x, where g of x is given and f is unknown. The solution f consists of antiderivatives of g, which involve an arbitrary constant. In most practical cases, the differential equation is accompanied by an initial condition that allows us to determine that arbitrary constant. Therefore, we consider problems of this form, f prime of x equals to g of x, where g of x is given, and f of x is equal to b, where a and b are given. So you have your differential equation and your initial condition. So if you put the differential equation with an initial condition, we have what they call an initial value problem, like in this example number 17. For the function f given below, find the antiderivative, capital F, that satisfies capital F equally to 1. Okay, and in this case, we got f of x is equal to x to the fourth minus 2x to the negative 2 minus 4. So in this case here, if I'm finding capital F of x, that will have to be the integral of lowercase f of x dx. Here's what lowercase f of x is. There'll be the integral of x to the fourth minus 2x to the negative 2 minus 4 dx. So now we integrate as we normally would in those previous examples that we've been doing. So here, using the sum rule, I'd do the integral of x to the fourth dx, then minus That 2 is a coefficient of x to the negative 2. I can pull that out in front. So it'd be 2 times x to the negative 2 dx minus that 4 can go out in front of the integral sign. So it'd be 4 times the integral of dx. Now for each one of these, we're going to apply the power rule. So for that x to the 4th dx, we increase the power by 1, so it'll be 4 plus 1, which is 5, divided by 5, plus 2 times this integral of x to the negative 2 dx, we increase the power by 1, so it'll be negative 2 plus 1, which is negative 1, divided by your new exponent of negative 1, plus the 4 integral of dx would just be x, and then plus c. Now, if I simplify this a bit, I'm going to have x to the 5th over 5. 2 divided by that negative 1 will make that a minus 2. X to the negative 1 plus 4x plus c. Okay? Now, they do give us an initial condition. They do give us the fact that f of 1, or capital F of 1, and by the way, this is capital F of x, and capital F of 1 is equal to 1. What that means here is this. X is equal to 1, and capital F of x equals 1. So now we're going to substitute the x with 1 in this equation, and f of x will be replaced with 1. So capital F of x will be 1, and that's equal to every x will be replaced with 1. So this will be 1 to the 5th divided by 5 plus 2 times 1 to the negative 1 plus 4 times x, which is 1, plus c. That's what's going to help us find out what c is. So I have 1 is equal to, well, 1 to the 5th is 1, so I have 1 over 5 plus. Now, if you did 1 to the negative 1 in the calculator, let's see, 1 hat key negative 1, you're going to end up getting 1. So this is 1 times the 2, which is 2, plus 4 times 1, which is 4, plus c. Now, if I add 1/5 plus 2 plus 4, I'm going to do 1 divided by 5 plus 2 plus 4, then the math key, and then number 1 for the fraction, I would get 31. I take that back. This should be a, well, I was right. This should be a minus sign. Yeah. This should be minus. This should be minus. I apologize for that. So let me try this again. 1 divided by 5 in parentheses minus 2 plus 4. And then math, number 1 for fraction. That would give you 11/5. And I'm still wrong. Messing up on these signs right here. This should be minus as well. And then this will be a minus 4x here. Okay, that's a minus. This would be minus. That will make this minus, and that's minus. So this is what happens when you mess up on these signs. You can really mess up the problem big time. From here, there should be a minus sign here. That minus 2 will make that negative 1 a plus 1. So this will be a plus here. Or do I apologize for that? Mess up. Okay, let's try this again. 1 divided by 5 plus 2 minus 4. Math key, number 1 for fraction. Yeah, negative 9/5. So I have 1 is equal to negative 9/5 plus c. And then if I add 9/5 to both sides, that would mean C is equal to 1 plus, and in parentheses, 9 divided by 5, close parentheses, hit the math key and then number 1, you will get 14/5. So your constant will be the 14/5 for this f of x function here. So that means capital F of x would be this: x to the 5th divided by 5 plus 2x to the negative 1 minus 4x plus that constant of 14/5. So this is my capital F of x function, or the antiderivative that satisfies capital F of 1 equaling to 1. Okay? And I do apologize for these mistakes. So here I just pretty much messed up on the sign, so here I had to go back and correct that. All right, finally, example 18. Let's say we had f of x is equal to 4x cubed plus 6 sine of x. Our initial condition is capital F of 0 is equal to 3. And we want to find this antiderivative satisfying that given condition. So that means capital F of x is going to be the integral of f of x dx. Which means the integral of, well, f of x, that's the 4x cubed plus 6 sine of x dx. And in this case here, let's break this up here. That 4x cubed, I'll pull the 4 out in front and take the integral of x cubed dx plus, for the 6 sine of x, I'll pull the 6 out in front, so it'll be 6 times the integral of sine of x dx. This first part right here, I'll use the power rule. Bring the 4 down. For the integral of x cubed dx, I'll increase the power by 1, so it'll be 3 plus 1, which is 4, over the new exponent of 4, plus 6 times. Now go back to one of those tables for the integral of sine of x dx. Integral of sine of x dx, that's this right here, negative 6 cosine of x. Negative cosine of x, I'm sorry. So, integral of sine of x dx would be negative cosine of x, and then plus c. So if I was to write that, then there'll be capital F of x would be, and if I simplify this a bit, these 4's divide out. So you're left with just x to the 4th. This negative will make that plus 6 or minus 6 times the cosine of x plus c. But now we have an initial condition where f of 0 is equal to 3. That means if x is 0, then f of x, or capital F of x, will have to be 3. So we substitute those values into this equation here. So my f of x is at 3 is equal to, substitute your x with 0, so it'll be 0 to the 4th minus 6 times the cosine of 0 plus c. So now we got 3 is equal to 0 to the 4th is 0 minus cosine of 0. You have to look through your unit circle for the cosine of 0. That's going to be 1, so it'll be minus 6 times the cosine of 0 is 1 plus c. And if I do 0 minus 6, that's going to be negative 6, so it'll be negative 6 plus c is equal to 3. Add 6 to both sides, you'll get c is equal to 9. So that constant will be replaced in this f of x function up here. So I have capital of f of x is equal to x to the 4th minus 6 times the cosine of x plus 9. That would be the antiderivative that will satisfy that given condition where f of 0 is equal to 3. Okay? All right, so that does conclude this video on section 4.9 dealing with antiderivatives. Feel free to reach out to me if you have any questions about anything that was presented in this video or any of the homework problems that are in my math lab.